Okay, now we need to talk about graphing functions in more detail. So when we go to graph a function, it's really no different than graphing any xy equation. Again, because y equals f of x, so the f of x is just replacing the y. So if you graph any equation, you make all the points x, y that satisfy the equation and connect the dots. Well, to graph a function, you basically do the same thing. The graph of a function is the collection of ordered pairs x, f of x, such that x is in the domain of f. So if I go to graph anything, any function, so let's say f of x equals 3x plus 2. The general idea here is I have to find all the ordered pairs that satisfy this function, such that the first component is my x and the second component is f of x. So one way you learn to graph anything is to do an xy or xf of x chart. So we're going to do this xf of x chart, plug in some random x values, I don't know, 1, 0, -1, and find f of that. So f of 1 is 3 times 1 plus 2, so that gives me 5. F of 0, if I take this 0 and I plug it in here, f of 0 is going to give me 2. F of -1, if I plug this in here for -1, f of -1 is going to give me 3 times -1 plus 2, so -1. So then these are some ordered pairs that are x, f of x, that satisfy the function, or essentially are in the domain of the function as far as the x's go. So I put that in my x, f of x plane, which is normally x, y, but you know, your x-axis and your y-axis, but we have x, f of x now. So I go, okay, 1 for my x, 5 for my f of x, and that gives me this point right here. 0, 2, 0, 2 puts me right here. -1, -1, there's -1, there's -1, it puts me there. So I connect the dots and I get the graph. This should be a line. My graphs aren't great, but one thing you got to understand when it comes to the graph of anything, a graph is really just an estimate. It's only going to be as good as your graph is set up to be. So this graph is not the greatest graph, but it gets the job done in terms of this is the picture that represents that, and it should be a line. Okay, so one thing we need to start doing is looking at graphs in a little bit more detail, and then also coming up with better ways to graph things other than the XY chart, because that XY chart is just sometimes too time consuming. So let's look at some details first. We can label a graph as either increasing, decreasing, or constant, or a combination of the three. So let's look at the definitions first, and then we'll talk about how we can write them down. So a function is increasing on an interval if for any x1 and x2 in that interval such that x1 is less than x2 and f of x1 is less than f of x2. Now, you know, lots of times with these definitions you read them a bunch of times and they might not make sense, but simplest way to talk about increasing is that your graph is going up from left to right. You always read your graphs the same way you read a piece of paper. So the graph is going up from left to right, or down from left to right, or not changing at all from left to right, but we read it from left to right. So increasing, the simplest way to talk about increasing is it's going up from left to right. Now you could see this if I take a graph that is going up from left to right. Okay, this is my function, right? It's going up from left to right. Here's x1, here's x2. Clearly x1 is less than x2. If it's on the x-axis, it's to the left, so it's less than. Then I look at the corresponding y values. So there's the point for x1. This would be f of x1. And then here's the point for x2, so this would be f of x2. So you look at that and go, okay, well, clearly on the y-axis, or the f of x axis, f of x2 is bigger than f of x1. So x2 is bigger and f of x2 is bigger, and that would only happen if my graph is going up from left to right. So increasing, this right here is the idea of the definition, but really the easiest way to say is it's going up from left to right. So then you look at decreasing. Okay, so a function is decreasing on an interval if for any x1 and x2 in the interval such that x1 is less than x2, which is the same as this definition above, but here's the difference, f of x1 is now greater than f of x2. Now the simplest way to talk about this is the same, but in this case the graph is going to be going down from left to right. So if your graph goes down from left to right, it's decreasing. So here's a picture. Here's my x-axis, y-axis. Here's a graph that's going down from left to right. So there's my function. It's going down from left to right. Here's x1, here's x2, just random values. x1 is still less than x2, but look at the corresponding y values. Here's the y value, here's f of x1, and here's f of x2. Now f of x1 is bigger, and that's because the graph is going down, so the y value here is bigger than the y value here, and therefore it has to go down. We say that that's decreasing. And then the last one is constant. My function will be constant if for any x1 and x2 that are greater than or less than, doesn't really matter, the corresponding y values are the same. F of x1 equals f of x2. So if the y values are the same as you move from left to right, meaning my graph is horizontal, then I have a constant function. So, here's a graph, here's my horizontal line, here's x1, here's x2. The y values for both of them are equal. If they're equal, it's going across from left to right. It's not going up, it's not going down, it's staying horizontal from left to right. And therefore, we consider it to be a constant in that interval. Okay, so let's look at an example. Here are 3 different examples of functions, and some of them increase, some of them decrease, some of them are a combination of them. So if you look at this function right here, first one, this function here is x cubed, which we'll talk about in a little bit more detail in a little bit, but this is what the x cubed function looks like. If you look at it from left to right, now it's continually, it really should have arrows on the end here. But if I read it from left to right, it's going up the whole time. In this section in here, it might look like it goes horizontal, but it really never does. It's always still going up just a little bit the whole time. Well, that means it's increasing over the entire graph. And the key is find the intervals for which the function is increasing, decreasing, and I really should say, or constant. So the interval for which this thing is increasing, since it's increasing the entire time, is, I would say, it's increasing over the interval from negative infinity to positive infinity. So this function is increasing over the entire function, which means over the entire domain. The domain goes from negative infinity to positive infinity. Alright, let's look at the next one. So if we look at this function here, now it's x cubed minus 3x. How I came up with this graph is not that important right now. Right now it's just look at the graph. This graph is going up to this point right here, and then from there it's going down from left to right till I get to here, and then it's going up from left to right till I go here. And I think it's clear, everyone can see where it's going up and where it's going down, but how do I write down the intervals over which this thing is increasing, decreasing, or constant? Well, the way I can write this interval down would be to say, alright, let's do this. Let's take this, and I like to put a little dotted line where it changes, and another dotted line where it changes. Okay, and if you look at this, what I just did is I broke the x-axis into intervals. Here's one interval, here's another interval, and then here's another interval. Those intervals are the intervals I'm going to use to write this. Whenever it says find the intervals over which a function is increasing, decreasing, or constant. Really what it's looking for are the x values. So these are the x values that I'm looking at. So there should be an arrow on the end of these graphs. So this is going down to negative infinity, but if I read it from left to right, it's going up. It's increasing. It's increasing over the interval from negative infinity all the way up to this dotted line where it changes, and that has an x value of -1. Okay. Then from here to here, from this point here to this point here, it's decreasing, it's going down. Well, what are the x values between there? Well, it's -1 to 1. Okay, those are the x values for which this is happening. So I'm going to say it's decreasing over the interval from -1 to 1. Then it goes back up again from left to right. It starts going back up here at this point and keeps going up and up and up forever. So if you think about the x values for which this is happening, it starts at -1 and then goes all the way down to positive infinity. So then it's increasing again over the interval from 1 to infinity. So like I said, sometimes the easiest way to look at this is to sort of separate it and say, alright, here's the places where it's changing. Now I have these intervals that I can write down as far as the x-axis goes. The common mistake I see a lot of students make is that they'll use the point itself and say it's increasing from this point to this point, or in this case decreasing from this point to this point, but that's not the way you should write it down. You should only write down in terms of the x values, the domain values for which these things are happening, increasing, decreasing, or constant. Alright, let's do one more. Here's some random function. It's this piecewise function. Doesn't matter what the piecewise function is or how I came up with the graph. This is the graph. So if I'm looking at this function and I'm trying to figure out where is it increasing, decreasing, or constant, well, I think you can clearly see that it's going up there, it's horizontal here, and it's going down here. So if I put a line where the changes are, and I look at this and say, okay, if this is where my changes are, this one, I have it increasing. Put a little arrow on the end here. Okay, it's increasing, which we'll use a positive lots of times to denote that. It's decreasing here, we'll use a negative to denote that. And it's constant, lots of times we'll just use a 0 to denote that as well. And that has some correlation to some of the things you'll look at in calculus if anybody's going to take calculus. But if I want to write this, I'm going to say, okay, it's increasing from negative infinity to 0. That's the x value right here, 0. So it's increasing from negative infinity to 0. Parentheses, and I'll talk about the parentheses in a second. It's constant from 0 up to 2, and it's decreasing from 2 all the way up to positive infinity. Now these are intervals, so when you do intervals you can do brackets or parentheses, right? Brackets or parentheses. Bracket means included, parentheses means it's not included, right? So I put parentheses around everything. If you look at all these ones, there's parentheses around the whole thing. The reason why I put parentheses is I had -1, say for this function right here, -1, 1 are the changeover values. It's where it's changing from increasing to decreasing or vice versa. So I can't really include that in an increasing interval or a decreasing interval because it's the changeover point. Same thing here, 0, 2. These are the changeover values, the x values for which it changes. So I'm not going to include those in anything. So whenever you're doing these increasing and decreasing, typically we'll use parentheses around the endpoints because that's where it's not doing anything. It's changing over from increasing to decreasing or decreasing to increasing. The next thing we need to start looking at is families of functions. We don't want to have to always do an XY chart to graph everything. But if we start to learn how different types of functions look in terms of the shapes of their graphs, it will make it easier as we move through to try and graph different kinds of functions. So the purpose of the rest of this lesson is really to get used to learning what certain functions look like algebraically, as well as graphically what they look like. And by the end of this, you should be able to match each function with a picture or a graph of that function. So we start off with the simplest ones. The simplest one you can deal with is a linear function. So a linear function, the standard form of a linear function is this f of x equals mx plus b, which you should be familiar with as your slope-intercept form of a line y equals mx plus b. The slope of the line is m and the y-intercept is 0b. So if I wanted to graph that line, usually you could do an XY chart if you want, but the easiest way to do it is to use the y-intercept and the slope and the whole rise over run concept to graph the line. I'll show you an example in a second. One thing that happens with these functions is that the domain for every linear function is all real numbers. The range is all real numbers. Typically it has a y-intercept of 0b. And the graph is either increasing, decreasing, or constant depending on the slope. The slope being positive makes it increasing. A slope that's negative, it's decreasing, and a slope that's 0 would make it constant. You should be able to recognize linear functions. If I give you this function, f of x equals 3/2 x plus 2. You should recognize that as a linear function. It has that form y equals mx plus b. In this case, m being 3/2 and b being 2. So this is your slope and your y-intercept. If I wanted to graph this line, I should know that the graph of a linear function is a line. So knowing what the picture should look like before you start is pretty key to graphing anything. So the linear function, I know the graph should be a line because it's a linear function. If I want to graph this, I could do an f of x chart, but what I'm going to do is use another concept, which is using the slope and a point, in this case the y-intercept, to draw the graph. So I have this f of x, or remember this could also be y. I have a y-intercept of 2. So it's right there. But then I have a slope of 3/2. Now if I look at my slope of 3/2, I can also think of that as rise over run. So if I go rise positive 3, 1, 2, 3, that now puts me at 5. And then if I run 2, 1, 2, I'm now at this point. That was a rise of 3 and a run of 2. Okay? 3, 2. If I do that again, rise 3, run 2, I'll get another point, and another point, and another point, and I can draw my graph using those points. Again, I knew it was going to be a line because it was a linear function, and one way to graph these linear functions is with the slope and the y-intercept. If you don't like that method, you could always use the XY chart or f of x chart, but you gotta get used to this slope y-intercept stuff because it will come up again in other aspects. But this is one way to graph it. The key is I knew this was a linear function because this has the same form as that. There are two specific types of linear functions that come up, one called a constant function and one called the identity function. So you have your constant function and you have your identity function. Now a constant function is f of x equals c, c being just some number. So anytime you have f of x equals a number, okay, that's what we call a constant function. The graph of that constant function will be a horizontal line through this y value. Essentially what this is a y value, an f of x value. So if I said f of x equals 3, This is a constant function. Now it's a linear function still, but we consider this to be a constant function. I could also write this as 0x plus 3. So it's in that mx plus b form. So that's why it's still linear. The graph is still a line. And what it would be is, here's a 3 on the f of x value, or f of x axis. I would be this horizontal line through 3. This would be the graph of my function f of x. Another common function in terms of linear functions is something called the identity function. So if I look at this identity function here, the identity function is this function f of x equals x. Okay? If you look at f of x equals x, this is the same thing as x plus 0. You can think of it as, okay, the slope is 1 and the y-intercept is 0. If I go to draw this, what this line is, simplest thing, idea is, it's this 45-degree line basically that cuts the x, y plane in half diagonally. Every point on this line has the same x and y coordinates, so like 1, 1, 2, 2, 3, 3. These will all be points on this line. If f of x equals x, f of x and x are equal, which means that they're the same. That's where the 1, 1, 2, 2, 3, 3 come in. This line is going to be important when we talk about inverses. So just keep this in mind. F of x equals x is called the identity function. It cuts the xy axis in half diagonally, essentially 45 degrees this way, and this way is your 45 degrees. And we'll talk more about degrees and so on when we get to trigonometry. The next function we need to look at is the squaring function. The squaring function is simply just going to be f of x equals x squared, hence the name, the squaring function. Generally, the shape for all these squaring functions will be a U-shaped curve. We call that U-shaped curve a parabola. Okay. The domain for this function is all real numbers. The range for this function is not all real numbers, because when you square anything, you'll always get a non-negative value. You either get 0 or positive. So the range is all non-negative real numbers. This function, we consider this function to be even. That has something to do with the power, but mainly has to do with some of the symmetry of the function. We'll talk about that in a second. It has an intercept at 0, 0. That's both the x and the y-intercept. It's decreasing and increasing. It'll decrease from negative infinity to 0 and increases from 0 to infinity. It's symmetric with respect to the y-axis, and that has something to do with the fact that it's even. And it's got a relative minimum or a low point at 0, 0, which is the intercept. If you look at the graph of this function, it looks like this. This would be f of x equals x squared. Now I could come up with that graph by simply doing an x f of x chart, right? If I plug in -2, -1, 0, 1, 2, if I plug these values in, I could see what the y values are for these particular x values. And so I plug -2 in, I square it, I get -2 squared, which is 4, -1 squared is 1, 0, 1, 4. And if I look at these points, well, I got 0, 0, right? -1, 1. So there, -2, 4, so there, and so on, 1, 2, this will be 1, this will be 4. And what happens is I keep doing this, I'm going to get the shape of this parabola. Now here's the thing, anytime you have to graph another x squared, it should have the same shape. Okay. Now also, this idea of symmetry. If I look at the y-axis, okay, this y-axis cuts this graph into two equal pieces. This side and this side are symmetric. They're mirror images of one another. So this is symmetric with respect to the y-axis. If my function has that symmetry, we consider it to be an even function. Now that's not really important right now, but when we talk about trigonometric functions, symmetry comes into play. This idea of even functions or even odd functions will come into play a little bit more then. But for right now, what you need to understand is anytime you see f of x equals x squared, a squaring function specifically, the shape of the squaring function should be a parabola or a U-shaped curve. And now we may alter that curve a little bit by altering the function, but we'll get to that later. Right now you just have to recognize what function we have and what the shape of the graph is. Linear functions, the shape of the graph is a line. Squaring functions, the shape of the graph is a parabola. So if I give you a bunch of functions to look at, you should be able to recognize them as linear or squaring right now. Now we're going to keep adding to that list. The next function up is the cubic function. The cubic function is f of x equals x cubed. Now this is different from the squaring function, has a different shape. The domain is the same, the range is different. This function is considered to be odd. So if we look at this cubic function, f of x equals x cubed, the domain is all real numbers. I can plug any value in here for x and I'll always get an answer. The range is also all real numbers, in that I can get positive, negative, zero values out of this thing. I can cube a negative, I get a negative. I cube a positive, I get a positive. I cube 0, I get 0. So I can get all kinds of numbers out of it. The range is all the outputs, the y values. So that's all real numbers. This function is considered to be odd. Now that has a little bit to do with the power, but also has something to do with the symmetry again. We'll talk about that in a second. Has an intercept at 0, 0. It's both the x and the y intercept. This function is increasing the entire time. We saw a graph of this function just a few minutes ago. And this graph is symmetric with respect to the origin. The squaring function was symmetric with respect to a line, the y-axis. This function is symmetric with respect to a point, the origin, 0, 0. So look at the graph. If we look at the graph of this thing, it looks like this. Okay, this would be f of x equals x cubed. Again, I could come up with that graph right now just by doing an x f of x chart. Plug in some x's, just random, -2, -1, 0, 1, 2. Figure out what the y value is, -8, -1, 0, 1, 8. So I connect the dots and I get, essentially something that looks like this. You can see that this function is increasing over the entire graph. We talked about that already. Anytime you see a cubic, we have any cubic that we have is generally going to have this same shape to it. So if you look at this cubic here, it's got this shape, and we call it a quadratic or a squaring function, a parabola. This really doesn't have a name to it. We just call this the cubic shape. But anytime you see a cube, you got to think this shape, this snake shape, this S shape, whatever you want to call it. This is the cubic shape. Now, we talked about this as being symmetric with respect to the origin. So what does that mean? It's not symmetric with respect to a point, or with a line, but with respect to a point. So this is the easiest way to think about symmetric with respect to a point. If you were to fold your paper once, if you look at the parabolas look like this. If you fold your paper once along this line right here, this side would match up with this side. But cubics, if you look at a cubic, cubics are symmetric with respect to a point. So what it really is a series of two folds. If I folded my paper along this line right here, the y-axis, this piece right here would fold over to here, right? This would come over here if I folded my paper over that way along this y-axis. This piece does not match up with the other piece like it did with the parabolas. However, if I fold my paper again this way along the x-axis, this piece here would match up with this piece here. And through a series of two folds along the y-axis and then along the x-axis, I could get this piece to match up with this piece. Well, what's the thing that those 2 points, those 2 lines have in common? This point right here. So we say that this function is symmetric with respect to this point. Next function up is the square root function. Square root function called square root function because it's f of x equals the square root of x. Has some features. Domain, not all real numbers. It's only non-negative real numbers. You can only take the square root of 0 or positives. So the domain is only the non-negative real numbers. The range, same thing. Those are the only answers you'll get out of the square root function. The graph has an intercept, 0, 0. Both the x and the y intercept the same point, 0, 0. And the graph is increasing over its entire domain. The domain is 0 to infinity. So if we look at the graph of the square root function, it looks like this. And this would be f of x equals the square root of x. If you see, it's increasing, but the domain is only, if you look at this, is only from an x value of 0 onward to positive infinity. There is no graph over here. Okay, this is the negative x-axis. I can't plug any of these x's into this square root function, therefore the graph isn't located over here. It has this curve to it, right? This is not a line, this should be a curve. It curves upward like this, and increases slower and slower. It curves up slower and slower as we go out, but it's always pointing up just a little bit. This would be the graph of the square root function. So whenever you see the square root of x, okay, the key is this is an x to the first power, the square root of x to the first power. This is what the square root function should look like. So you know what a linear function looks like, you know what a quadratic function looks like, or a squaring function, you know what the cube function is, and you know what the square root function is. A special sort of circumstance of a square root, it's not really a square root function, but there's a square root involved, is the semicircle function. The semicircle function is this function here. F of x equals r squared minus x squared. Now you can see that this is different because x is squared. Now r is going to be just a number. Okay, so this would be something like the square root of 4 minus x squared would be an example of this semicircle function. We call this a semicircle function because the graph is really the top half of a circle. Okay, so the domain is going to be any value for which this entire interior is greater than 0. So this is the interior. It should be really greater than or equal to 0 because it could be equal to 0 as well. The range is all the non-negative real numbers, and the graph is going to be a half circle. So the way you do this is this. If you look at r, this is r squared, right? So that tells me that r equals 2. From the, the general form of this thing. If you look at r is r for a reason, is really what it is the radius of a circle. Now this is just half of a circle, but that's what that represents. So take whatever this number is in here, the square root of it will be the radius of your circle, and just draw the top half of that circle centered at the origin. So here's the center of the circle. If I go out 2 units, here's 2, here's 2, here's 2. That's 2 units in each direction. This circle has a radius of 2, and that should be a circle. My pictures aren't the greatest. But this is my circle. And it's a semicircle. It's the top half of the circle, radius 2. There's a radius of 2 in all directions out here. That would be this particular function. If I gave you another one, if I said, how about we do f of x equals something else. Let's go f of x equals the square root of 9 minus x squared. It's always going to be some number minus x squared inside here. And that's the difference. The last one, the square root function, was f of x just equals the square root of x. Right? In that case, it's just x to the first, and that's the square root function. Here we have 9 minus x squared, so that's telling me this is not the square root function, but the semicircle function. This value right here is r squared, therefore r equals 3. Right? Take the square root of 9, you get 3. I have a semicircle where my radius is 3. So I go 3, 3, 3 units away from this center point. That's 3 units in every direction. Draw your semicircle, and that's the graph. It starts on one end, ends on the other end. So if you look at this graph, it's increasing to here, then decreasing to here, but it's this top half of a circle. Now this number inside here does not have to be a perfect square. Let me give you one more. If I said f of x equals the square root of 5 minus x squared. If you think about it, this is r squared. It's the same thing as every other one. I just didn't use a square here for this number. It's a 5. But if r squared equals 5, that tells me that r is the square root of 5. So that's my radius, which is no big deal to draw it. You just go square root of 5 out from the center. So here's square root of 5, here's square root of 5, here's square root of 5, away from the center, connect your dots. This is your half circle here. Okay? So it starts here, ends here. That's that semicircle. Now square root of 5, if you think about where that's located, square root of 4 is 2, square root of 9 is 3, so square root of 5 is somewhere between 2 and 3, closer to 2. But that's the semicircle. So this number right here does not have to be a perfect square. It could be any number. That's going to be r squared. Take the square root of that number, that's your radius, and draw the top half of your circle. But you got to recognize the difference between this and this. Okay? This one is this number minus x squared inside the square root. This one is just x to the first power inside the square root. Next function is the greatest integer function, often referred to as the step function. Or we could also consider this thing to be the floor function, or even the round down function, as I like to call it. Now, round down is not an official term at all. Typically you'll see greatest integer, step function, or you'll also see it considered to be the floor function. So this is the notation. The notation is this double barred bracket. So when you look at this double barred bracket, you would see this floor function, or this step function. This is not absolute value at all. It has nothing to do with absolute value. It's just a notation, these double bars. So what the step function is it's the greatest integer less than or equal to x. Integer. An integer is a positive or negative whole number, or 0. So what this does is it takes everything you plug in and it rounds it down to the closest integer, the closest positive or negative whole number, or 0. So that's why I like to call it the round down function. So one thing you can look at is, let's evaluate a couple of things here. So if I say, let's find f of x is this step function, okay? And let's evaluate f of 0.2. So if I plug 0.2 into this function, what happens? Well, I should round 0.2 down to the closest positive negative whole number, or 0. So if I round it down, I would get 0. Try 5 halves. If I plug 5 halves into this function, what would happen? Well, I have to round it down to the closest positive or negative whole number, or 0. 5 halves is 4.5. Or sorry, not 4.5, 2.5. So if it's 2.5, I round it down, I would get 2. How about f of, I don't know, let's do 0.999. Now, while 0.999 is actually closest to 1, if I have to round it down, I have to round it to the less than or equal to value. The closest one down would be 0. So I'm rounding it down. If I look at it on the number line, okay, here's 1, here's 0.999. I always have to round down to the closest integer. So let's do one more. F of negative 4.1. If I plug negative 4.1 into this function, I have to round it down. So negative 4.1. I have to round this down to the closest integer. And what a lot of people will say is negative 4. But if you really think about it, here's negative 4, here's negative 5, here's negative 4.1. If I round down, I always move to the left. The one to the left would be negative 5. So this rounds down to negative 5. So this is what it looks like to evaluate this step function. Okay, so now we need to graph this function. Now there's a reason why they call it the step function. If you look at the graph of this function, it looks like steps. So if you think about it, okay, if I take an x value of 0 and I plug it into this function, I'll get 0. If I take an x value of 1 and I plug it into this function, I'll get 1, because these are whole numbers and it should stay the same if it's a whole number. It doesn't round down, it stays the same. However, if I take any x value between 0 and 1 and I plug it into this function, I'll get 0. I'll get it to round down to 0. So all these values in here give me all the same y value. The second I get to 1, I jump up to 1. So I put an open circle here to show it's not included, and it jumps up to here. Now if I plug any x value between 1 and 2 into this function, those are all going to be rounded down to 1. So then it looks like this, and then jumps up to 2, and then so on and so on. And this is why it looks like steps. And the same thing will happen on the other side. It'll look like this. And so you have the series of steps. Each one's going to be at a particular whole number, positive or negative, depending on what value I'm plugging it in. Okay, one of the last major functions that we need to cover is a piecewise function. So we talked a little bit about a piecewise function before, and the idea is a piecewise function is just a function that's defined with multiple functions in one, so separate pieces. The key to a piecewise function is that you have to know which piece to use when. So if you look at it, we have 2x minus 3 when x is less than or equal to 1, and negative x plus 4 when x is greater than 1. Now, piecewise functions don't have to be defined by certain functions all the time, in that if you look at this one, this function has two linears, a linear for this piece and a linear for this piece. They're both in the form of mx plus b. They don't have to be linear. You can have one piece that's quadratic, one piece that's linear, one piece that's cubic. It doesn't have to be two pieces, it could be three pieces. Since we're beginning right now, we're going to talk about some simpler ones, so linear for each piece. But the key is this right here, the domain. You have to know which x's go with which piece. The easiest way, I think, to graph these is to look at your xy chart, or your xy plane, and then look at the break. Where one changes to the other, you have x is less than or equal to 1 for one piece, x is greater than 1 for the other piece. So the break is at 1. So I'm going to put a little dotted line right here. Now this dotted line has really not part of the graph, it's just showing me where the break is. So the idea is on one side of this, when x is less than or equal to 1, I should be looking at the function f of x equals 2x plus 3. And on the other side of this break, x is greater than 1, I should be dealing with f of x is negative x plus 4. So what I'm going to do is graph this function on this side and graph this function on this side. And that's how I'm going to graph the entire piecewise function. So if I start to look at this here and I say, alright, well, let me do one at a time. So if I graph 2x plus 3 over here, well, think about this. The slope is 2 and the y-intercept is 3. So 1, 2, 3. There's my y-intercept. So that's one point. The graph is a line because it's linear, and at this point you need to be able to see that this is a linear function, therefore the graph is a line. So I can go up 2 spaces and run 1 space, and that puts me here. Now I'm going to use a solid circle here. Why am I using a solid circle? Well, because this is or equal to, which means x can equal 1. When x equals 1, this is the point I get. So I'm going to then connect the dots, and that's my graph, but only on this side. I'm not going to let the graph travel over to the other side. So that's my piece over here. Now look at my other piece. My other piece is f of x equals negative x plus 4. Okay? That has to be graphed on this side. So I can do the same thing, y-intercept and slope, but I really want to stay on this side. So I think for most students it would probably be easier to just say, alright, let's do an f of x chart. Okay? But I'm only going to use x's that are over here, so 2, 3, 4, and so on. So if I plug in 2 or I plug in 3 for x, what am I going to get? Well, if I plug 2 in for x, I'm going to have negative 2 plus 4, so 2. Plug in negative 3, I'm going to have negative 3 plus 4 is 1. So I have these points 2, 2, 3, 1, and that's going to be points that are going to make up this piece of the graph. So I connect the dots and I get this piece of the graph. Okay? Now here's the problem. I can use any of these x values too, because all these x values right here are all bigger than 1. So what's going to happen is my graph is going to continue going this way. But the second I get to an x value of 1, I now jump to the other piece. The way I can describe that is by using an open circle here. So this one has an open circle at the end, this one has a closed circle at the end, and that's going to be based off of my greater than or equal to or less than or equal to, or wherever the or equal to is. The or equal to will get the solid, the no one without the or equal to gets the open circle. And this is the graph of my piecewise function. One piece on one side, the other piece on the other side, the break being at 1. Now you don't need this dotted line right here. I just put that in there so you see where each piece goes. One piece on one side, the other piece on the other side. Now your two pieces don't have to be two lines. I mean, I could draw a piecewise function. Let me erase some of this. I can draw a piecewise function where one piece, if you look at it, say something like this, say this was my breakpoint 2. On one side my piece was a parabola, and on the other side it was just a line. Okay, but the key is, if you look at kind of where they line up over top of the two, one of them has a solid circle, one of them is an open circle. If they were both solid, I wouldn't pass the vertical line test, and therefore wouldn't be a function, and one x would have two y's. Can't happen, remember. So one of these has to be a open circle. So open circle, something like that. That would be another piecewise function where one piece is a quadratic possibly and the other piece is a linear. For right now, most of the ones you're going to see are going to be like this, where they're linear in both cases. Piecewise functions really throw students off a lot, but if you just think about it as two graphs on one xy plane, where one graph is on one piece of the plane, the other graph is on the other piece of the plane, I think you'll be better off. Okay, the most common piecewise function that you'll ever deal with is the absolute value function. The absolute value function which is this f of x equals the absolute value of x, is really a piecewise function because we define an absolute value in pieces, really. If we look at the absolute value of x, the absolute value of x is defined in two pieces. X for x is greater than or equal to 0, or negative x for x is less than 0. Okay? So it looks like a piecewise function where both pieces are linear, and the idea is lots of people think the absolute value just makes everything positive, which in a way it kind of does, but what it really does is it represents a distance, and essentially what you think of is the absolute value of x. If x itself is greater than or equal to 0, then the answer is just whatever's inside the absolute value. If the thing inside the absolute value is negative, is less than 0, okay, then we have the answer to be a positive answer, right? But if it's already negative, if x is negative, and I multiply it by a negative, I now have negative x, or which is now a positive value. But if I think about this as my function, right, it's two pieces. The break is at 0. So here's my 0. That's where my break in my graph is going to be. On one side, when x is greater than or equal to 0, I have to graph f of x equals x. When x is less than 0, I have to graph f of x equals negative x. So this gets graphed on one side, this gets graphed on the other side. So if I graph f of x equals x, slope of 1, y-intercept of 0, because this is really plus 0. So the y-intercept's at 0, I use a solid circle, because that's the or equal to 1. A slope of 1, so go up 1, over 1. So this is my point, this is my line. On the other side, y-intercept's also 0. Slope is negative 1, so I go up 1 and to the left 1, so I'm here. Now, this is going to be my line. Now, the second I get to this point, I'm going to have an open circle. Now, there's an open circle on top of a closed circle, so it looks like it connects, but that happens sometimes. You look at what this graph is, this is a V shape. Every linear x to the first power absolute value will have this V shape to it. So add that to your list of functions whose graphs you know the shape of. So we have our linears are just lines, our squaring ones are going to be our parabola shaped, we have our cubic shape, we have our semicircle, we have our square root, we have absolute value, we have our piecewise. So we'll take a look at all of them and when we wrap this up. So one more function to go. The cube root function. Cube root function, not a common one that you're going to see a lot, but just to give you what the graph looks like real fast, it looks like this. Okay. If you cover this part up here and just look at this piece looks a lot like the square root function. The difference is, when it comes to cube roots, it's an odd power or an odd root. You can take the odd root of negative numbers. So all these negative x's, I can plug into this function and I'll get a negative answer. So I get this other branch of the root function, and therefore I get this cube root picture. So this would be the cube root graph. So if we summarize all our graphs, f of x equals mx plus b, linear. Linear, the graph is a line, either increasing or decreasing, going down or horizontal, depending on the slope. F of x equals x squared. Parabola. Like that. U-shaped. The point of the bottom point of the parabola is at the origin. F of x equals x cubed is our cubic function. So that has this shape to it. This is this cubic shape. What else do we have? We have the square root function. That's f of x equals the square root of x. That one looks like this. Okay. We have our semicircle function, that's f of x equals the square root of r squared plus x squared. That's gonna, actually minus, that's key, minus x squared. That's gonna be this top half of the circle, the radius of the circle depending on r. We could do the step function, that's this absolute value, not the absolute value, it's the step function where you have the double bracket bar. In that case, the graph is my steps. Remember, it looks like this: open circle, closed circle, open circle, closed circle, open circle, and so on. And it keeps going in either direction. Right, now we have the absolute value function, which is my V shape. And the last one is my cube root function, which looks like this. So those are your basic functions, and really by the end of this section you need to understand which functions go with which shapes. And if you can do that, then you're set up really to do the next thing, which is transformations of these functions.